Hello and welcome to Tuesday's edition of Cracking the Cryptic. Where have we got a puzzle for you today? This one is apparently an absolute work of genius. It's by Lizzie01. It's called 4 Lockout Lines, and you can see there is not a lot of information in terms of digits in this puzzle. We've got some tiny thermos, some lockout lines, an arrow, and a little killer clue. And I suppose that diagonal as well. And that is all. And apparently this is just a gem. So we should be in for an absolute treat, as usual, on the channel. I've got a couple of things to tell you about, though, before I read you the rules. Now, what were those things? Let me remember. Oh, yeah. Let's start with something. Today is Fibonacci Day, because it's the 11th month and it's the 23rd of the 11th month, so 1, 1, 2, 3. And Brian Bilstein, I think I mentioned this poem last year, but he tweeted it again this morning, and I have to share it with you because I just view it as such an absolutely beautiful thing. So Brian Bilstein's Fibonacci poem: I wrote a poem in a tweet, but then each line grew to the word sum of the previous 2, until I began to worry about all these words coming with such frequency. Because as you can see, it can be easy to run out of space when a poem gets all Fibonacci sequency. And if you count the number of words in each line, you of course get the Fibonacci sequence. And he's managed to fit it in a tweet as well, which is also something skillful. I absolutely love that. Brian Bilstein, there you can see his Twitter handle. Absolutely brilliant poet. So that was the first thing I wanted to mention because it made me smile. Oh, the next thing. We're going to be streaming Bubba Is You Friday night, 10 o'clock UK time. Mark and I will recommence our battle with that game. So if you've been enjoying those streams, we'd love to have your company. Now, the next thing, I had fun last night because I worked through some of the pencil puzzles that now appear on the special Discord channel. So over on Discord, there is a channel devoted to sort of pencil puzzles now, and every day a world-class constructor, people like Shy, Eric Fox, Tirganis, Jovial, are producing one pencil puzzle a day, just like the Gas series for Sudoku. You can play them totally free, and they're gems. And I worked through about 10 of them last night, and I've put that video of me doing those puzzles over on Patreon. So check that out, and do check out that channel on Patreon, on Discord. They are absolutely, it's really worth your time, and the puzzles don't take very long, especially not if you're experienced at them. Although I've noticed that some of they're definitely exploring the whole panoply of different Japanese puzzle types over there. There are many I've not seen before. I had to do, what was it I had to do yesterday? A look air, which I'd never done, and something called a Taz square, or tar square or something. Anyway, yeah, great stuff. Another thing to mention, the World Sudoku Convention, or Stroke World Puzzle Convention, has just finished, and I know you'll be familiar with some of the great names that were involved in that, but all the puzzles from that competition are now playable, and I'll put a link under this video for anybody who wants to go and have a look at that over on Logic Masters India. And I'll also going to put a donations page, because all of the constructors for that tournament, they're working pro bono, it would be nice if anyone out there feels like sponsoring or just donating towards that event. Is definitely a worthwhile cause. And the only other thing to mention is something Mark sent me, which I was rather tickled by, which has just come up in our merchandise shop. A Bobbins cap. Oh, Bobbins! I'm going to get this on my golf balls as well. I think it's a suitable thing. If I lose a golf ball, that's the sort of thing I might say. But anyway, it's coming up to Christmas. My ambition in life, it is one of my ambitions in life, is to actually see somebody in real life wearing Cracking the Cryptic merchandise. I don't think it will ever happen, but maybe one day if we can get this sort of thing popular. But I thought some of you might enjoy that, or you might know somebody who would. Now, that's all I have to tell you. So let's get on with 4 lockout lines. I believe this puzzle is very hard, by the way, so this is probably a very long video, and I apologise in advance for all of the logical missteps I'm about to make. Here we go. Normal Sudoku rules apply. Along thermometers, digits must increase from the bulb end. So let's stop there. There's a thermo there. So if we put, 3 in there, this square would have to be higher than 3. 5, that square has to be higher than 5. 7, that could be an 8 or a 9, and that would be a legitimate way of filling that thermometer. Digits along an arrow must sum to the digit in that arrow's circle. Now I think, staring at this grid, there is only one arrow, and it's this one. So those 3 digits add up to that cell. That's how the arrows work. The clue outside the grid gives the sum of the digits along the indicated diagonal. These digits may repeat if allowed by other rules. So we've got a 42 diagonal here. So those 9 cells there add up to 42. And we can repeat digits, so if that square was a 2, that square could be a 2 as well, no problem. But obviously what you couldn't do is put a 2 there, because those 2 2s would break the rules of Sudoku. The main diagonal marked in blue cannot contain a repeated digit. Okay, so we've got a difference in the diagonals here. It's quite a rare thing, this, in Sudoku. So this diagonal cannot contain a repeat. But this diagonal actually must contain a repeat, mustn't it? Because if it didn't contain a repeat, it would add up to 45, because that's the secret. The numbers 1 to 9 do add up to 45. Right, and we're just left with the lockout line rule now, which is the following. Digits on the diamond endpoints of a purple line must have a difference of at least 4, and the remaining digits on the line cannot be equal or cannot be between or equal to the digits on the endpoints. So, what does this mean? If this was a 3, this would have to be at least 4 different. So that would have to be at least 7. And now the digits on the line cannot be between 3 and 7 or 3 and 7 themselves. So they would have to actually be 1, 2, 8 and 9 in this example. That would be forced as to what goes onto the lockout line. So the way, I find it very difficult actually to get my head around lockout lines, but the way to think about them is basically, yeah, look at the numbers on the diamonds, and then everything outside is what's possible inside the line. We'll see how this goes. Do have a go yourselves. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. And I've got to be honest, the first thing that strikes me when I look at this grid is Fibonacci. Because whenever I see anything 2 by 2 like arranged in sort of symmetrical positions like this, I do think about either Fibonacci itself or some variant of Fibonacci. The variant of Fibonacci that applies in this situation is that those cells there are the same digits as these, I think. If I do use this, I'll prove it, of course, but let's just have a quick stare at that and see if we can see why that might be important. So that's telling us that the cells on the thermos appear in the lockout line diamonds. But that's, in fact, that's not actually surprising. This is probably not telling us very much, because if we think about it, whatever's in the lockout, in my example, where I put 3 and 7 in there, then it's not surprising. We know the lockout line itself would have 1, 2, 8, 9 on it here. And we know this cell couldn't be a 3 or a 7. So the 3 or the 7 is forced onto the thermo anyway. So this actually, I'm slightly surprised, but I'm not sure this is important. Right, let's remove that. Let's remove that and ignore the fact I just ventured into Fibonacci. Well, let's start with this then, because I can do something with the arrow in the middle. That's a 3-cell arrow. Those 3 digits all have to be different. So the minimum they could be would be 1 plus 2 plus 3. So this square is at least equal to 6. It's astonishing that this has a unique solution, actually. It's astonishing. There's nothing to get your teeth into here. I mean, there really is nothing. So do we have to... Let's go back to my example. Sorry, I'm just going to try and think about these lockout lines a bit more. What we know what we know is that whatever we put in the diamonds, we lock... okay, the diamonds have to be four apart, don't they? Yes, they do. Right. So they have to be at least 4 apart. That's the rule. But that can't be an 8 or a 9, because there aren't enough digits locked out if we do that. Because we know this is a 4-cell lockout line. So there must be 4 digits locked out. And if we go 3 and 8, now the only digits I could put in there would be 1, 2 and 9. Phone is buzzing. That's okay, it's not important. So that's impossible, because 1, 2 and 9 we would definitely have to repeat a digit. So we can actually say that these 2 digits are exactly 4 digits apart in this puzzle. And we can say that these digits always, wherever they go, end up on the thermo. They end up on the thermo. But does that matter at all or not? Hang on a minute. So in this example where we put 3 and 7 here, I've got to put 3 and 7 on the thermo. I've got to put 1, 2, 8 and 9 on the lockout line. So the 3 and 7 are actually the extreme digits of the thermo. Is that true? Is that always true? I think it probably is always true, because we know that the lockout lines must be the extreme digits. Yeah, so okay, that is always true. Oh, that's weird. Okay, so the 3 and the 7 in this example, but who knows what is actually in these diamonds. But whatever's in these diamonds has to be an extreme digit in terms of the digits that are left to place in this box. This can never be a 3 or a 7. 3 or 7 gets forced in here, and you can see that if we were to arrange the string of digits 1, 2, 3, 4, 5, 6, 7, 8, 9 in a line, we're always going to have extreme digits 1, 2, 8 and 9 on the lockout line, and then the next most inward digit is always going to be these 2 digits, and therefore they must be. So in this example you'd have to put 3 here and 7 here. But I think this works for, let's just prove it to ourselves. I think it's going to work for anything. So if we put, let's make these low. If that's 1 and 5, now 1 and 5, well, then we know the lockout line must be 6, 7, 8 and 9. So we know the extreme digits of the digits that are left are the 1 and the 5, because we've only got 1, 2, 3, 4 and 5 left. This can't be a 1 or a 5. We've got to put 1 or 5 on the thermo, so we'd have to do it exactly the same way. That set of digits is therefore, I was going to say, is always a consecutive sequence. It's clearly a consecutive sequence. Oh, a C. And it's on the blue it's on the blue diagonal. Right, that is suspicious. I don't really want to use that example though, because I think it was actually better when I used an intermediate example. When you're using sort of a very binary example like that, I'm not sure I'm not learning as much from doing that. So I'm just going to go back to this one. Yeah, 4, 5 and 6. So that yes, that makes sense. So it's the digits in between the digits in the lockout line that get shifted onto the diagonal. That is mad, Lizzie. That is crazy. So for this pattern, it's really very clever. It's really very clever. I can sort of see how Lizzie has thought about this. So by using a thermo, you can force the next 2 extreme digits off the diagonal and force the diagonal to be a sort of Renban. So in this case, these are going to be the digits between these digits. But that's the case because this is all symmetrical. Yeah, it is all symmetrical. Look where the bulbs and the ends are for the thermos. They're always off the diagonals in their boxes. That's gorgeous. So in every one of boxes 1, 3, 7 and 9, there is a consecutive sequence in these cells. Let's highlight them. These are always a consecutive sequence of digits that sit between the two digits in their lockout line, or the lockout line that points at that box. Now, I think that's going to be more interesting for this diagonal, which cannot contain a repeated digit, because now we know that that is a sequence of 3. We don't know what the sequence is, but that's another sequence of 3 that's got to be a different, it cannot have any digit in common. Yeah, I've got it, I think. I think I've got it. Right, let's ask a silly question, but it might help us to understand what's going on in the puzzle. These digits are always digits that are between whatever we put in the lockout line diamonds. So, what digit can you never put in an orange square, ever in this puzzle? You can never put a 1 in it, and you could never put a 9 in it. Because if you did put a 1 in one of these, it would have to be a 1, 2, 3 triple, and you'd have to put 0 and 4 in those squares. Now you can't put 0 in a Sudoku. It's simply impossible to have a 1 in one of those squares, and it's simply impossible to have a 9 because of the logic we've already described. Let's do it the other way around with high digits just to reinforce this. So 5 and 9, that would be a valid lockout line. This would have to be a 1, 2, 3, 4 triple, and this has no ability now. These three, well, you've got to put 5 and 9 onto the thermo, into those positions, and those squares have to be 6, 7 and 8, the digits between the lockout line diamonds. So yeah, this is very interesting, because that means that on this diagonal 1 and 9 is in the central box, and oh, this is ridiculous. This is ridiculous. Right, 1 and 9 are in there. So what does that tell us about this arrow? Well, this arrow can't have a 1 on it, so it must be a 2, 3, 4 arrow, and that squares a 9, and we have our first digit. I love this so far. This is extraordinarily clever. This is Fistimofel-esque, actually. That's probably the best adjective I can use to describe it. This is a puzzle that I think Fistimofel would absolutely approve of. Having said that, okay, right, so one of these is, yeah, okay, so this is telling us that on this diagonal here, we can't put a 2, 3 or a 4 in the central box, so there is a 2 somewhere in orange. Now once there's a 2 somewhere in orange, we know orange must be in a consecutive sequence, so there must be a 2, 3, 4 either up here or down there. 2, 3, 4. Okay, but we don't know what the other one is. The other one is either a 5, 6, 7 or a 6, 7, 8, but I don't know which way up this goes. 2, 3. So there's got to be a 2, 3, 4 in one of these, in which case, if it was here, if this was a 2, 3, 4, we wouldn't know the order. Let's just figure out what this means. If this was a 2, 3, 4, that would have to be a 1, 5 pair. This would have to be a 1, this would have to be a 5. And the lockout line would be 6, 7, 8 and 9. Don't know. don't quite understand how to make use of that. And the other one, and this of course could be down here, so this is, I'm just doing this so I can visualize it a bit more clearly. If this is either going to be 5, 6 and 7 or 6, 7 and 8, which means the lockout lines that surround this, if it's 5, 6, 7, it's a 4 and an 8 into those two squares. If it's 6, 7, 8, it's a 5 and a 9. Okay, I'm not sure. I'm not sure what to do with that. I'm really sorry. That's very difficult to. I really don't like as well, because the fact is I don't know which side, whether this is 2, 3, 4 or this is 2, 3, 4, and then even if I did know that, I wouldn't know the composition of digits in the other one, because it could be either 5, 6, 7 or 6, 7, 8. Oh, okay, so those two squares then are restricted. There's definitely a 1 in one of them. And the other digit is the digit I miss out of the 5, 6. So if it's 5, 6, 7, I've missed off 8. And if it's 5, 6, 7 here or here, I've missed off 8. And if it's 6, 7, 8 here or here, I've missed off 5. Okay, so these squares are from 1, 5 and 8. Which means is this mod 3? Oh, good grief. I think we can restrict those two digits. I think we might be able to use the 42 because what do we know about 3 consecutive digits? I think I talked about this yesterday. 3 consecutive digits, if you sum those digits, you always get a number that's divisible by 3. And that's just because of elementary algebra. Let's imagine this one is the middle one of this sequence of digits. So this could be 5, 6, 7, this would be the 6. If this was 7, 8, 9, this would be the 8. It's the middle digit. So let's label this digit x. We then know in this sequence there is the digit x, there's a digit that's 1 less than x, so that's x minus 1, and there's a digit that's 1 more than x, that's x plus 1. So sum those 3 things up, you get 3x. In other words, in any consecutive sequence of 3 digits, those 3 digits, when you sum them, you get a number that's divisible by 3, because it's expressible as 3 times a number. Now, why does that matter? Well, we're told this diagonal sums to 42, which is also mod 3. It's divisible by 3. So if those are divisible by 3, and those are divisible by 3, and the total for the whole diagonal is divisible by 3, these 3 squares are divisible by 3. Well, 9 is itself divisible by 3. So that means those 2 squares, I'm going to highlight them, these 2 squares are, if we sum them, we get a number that's divisible by 3. Now the options for these squares are not 1, not 2, 3, 4, not 9. So 5, 6, 7 and 8. So the beautiful, and this is beautiful setting, the thing that's interesting here is that 6 is the only one of these 2 digits that is itself divisible by 3. So if we were to put 6 here or here, we couldn't make the 2 digits together divisible by 3, because the other one wouldn't be. So that means there's no 6 on this diagonal. And that means where does 6 go in the box? It goes here. That is ridiculous. Oh my god. And there's a 7 on this diagonal, for certain. But 7 can go with the 5 or the 8. So it's either 7 plus 5 equals 12, or 7 plus 8 equals 15. Yeah, okay, and that makes sense, because we know that the other diagonal has got a 5 or an 8 on it. Wow. Just wow. Okay. So now, well now I'm wondering if we make that a 7-8 pair, this would be a 9-7-8 triple, which is 24, which means these squares would have to sum up to 18, which would mean, given they're a consecutive sequence, that cannot include a 1, because you can never, we've already worked out, you can never have 1s on these strings. This would have to be double 2, 3, 4. We'd have to, so if this has got a 7-8 pair here, this has to be 2, 3, 4, that has to be 2, 3, 4. We got 1s. Oh, hang on. I want to be a bit careful here, because this is conjecture. Well, as is this, but this is conjecture upon conjecture, which I don't like the feeling about. So let's just think about whether or not, if this is 9, 7, 8, you can really have 2, 3, 4, 2, 3, 4 on the other strings, or the other 3-cell limits of this diagonal. So you'd have to have 1s and 5s into those squares for sure. So you'd have to have 1 and 5. Well, you'd have to have 1 there, you'd have to have 1 there, you'd have to have 5 here, you'd have to have 5 here. This would be absolutely forced. I can't see what's wrong with it. There could well be something wrong with this. What did we know about the other diagonal? Oh, the other diagonal also had a 2, 3, 4 triple on it somewhere. So we're going to have okay. So we're going to have another diamond. One of these two diamonds here is definitely a 1-5 pair in this puzzle, because we know one of these strings is a 2, 3, 4 string. So if you had another 1-5, is that a problem? I can't actually see. I can't see why it's a problem. I'm just going to put this in. This green 1-5 could be there. So, but I don't think that's going to change very much. Let's just take a look at this and see if we can see it, why this might be a problem. So I still can't see why it's a problem. Apologies, I'm feeling a bit. So we get that sort of pattern. That doesn't work. You can't put 5 in the middle box now. Is that the same the other way round? So if we go 5, 1, 5, 1, 1, 5. Oh, it is. That's so weird. I feel like I should be able to see that, but I can't. Yeah, I'm struggling to see that clearly. So the 5s, because, yes, I think I do see it now. Whichever one of these is the 5, oh yeah, I do see it, finally the light has dawned. Whichever one, we know there's a 1-5 pair in one of these. Now, whichever one of these is a 5, let's just look at this one, because I've already pencil marked it in. What happens if this is the 5? Well, the key point is it pushes 5s into those two. If this is a 5, on the other hand, it pushes 5s into those two. So you always end up pushing a 5 in box 5 into this cross, where it cannot go. So this is broken. And it would be exactly the same if we don't have the 1-5 here, but we push them there. The logic is completely symmetrical. If that's a 5, you can see that the effect of that is going to be that those two squares have to be 5s, and it's the same. You get a 5 in the cross, which you can't have, and this is perfect. This is absolutely perfect, because this is going to get confusing now for me to understand exactly where we're going to unwind to. Well, what we've now proved is that this is not a 7-8 pair, because if it's a 7-8 pair, you can't put 5 in the middle box, and if it's not a 7-8 pair, then it had to be a 7 and a 5. So that is a 7 and a 5. That is a 1 and an 8. So we can get rid of some corner pencil marks. We can get rid of all of this now in boxes 3 and 7. All of that has to come out because it's wrong. And we have to take stock again. So we now know more things. We know more things than I used to know. And this is the great thing about cracking the cryptic. We learn about things that we learn things we didn't know before. And this is what extends life. Did you know that? Apparently, and there's scientific studies done, that basically, if you don't learn or have new experiences, your brain sort of almost goes into hibernation. So, like when I used to commute, I used to do the same commute every day. I never remembered the commute, even though I would have done different things on the commute and read different stories in the newspaper, because basically I was just in a loop. And my brain knew that's what I was going to be doing, so it sort of just went da-dee-da-dee-da-dum-dee-dum-dee-dum, day after day after day after day. So that time that I spent just elapsed. It had no quality. I have no memory of it. Whereas if you force the brain to learn new things and have new experiences, the brain gets sort of shocked out of its torpor, and you create memories, and those memories lead you to feel like time lasted longer. So this is why we need to constantly try and learn, because it makes us feel like our lives are longer. A good tip from cracking the cryptic. I hope I haven't put many of you to sleep. Right, anyway, what have we learned new about this puzzle? What we've learned is that this is a 189 triple now, and these are consecutive sequences, one of which is a 2, 3, 4, so the other one is a 5, 6, 7. But again, we don't know which way round they go. And the 5, 6, 7 must be bounded in its lockout lines, 5, 6, 7 by 4 and 8. So I can label these diamonds. This is a 4 or an 8, or a 1 and a 5, for sure. So 1, 5 is framing the 2, 3, 4. 4, 8 is framing the 5, 6, 7. I think that's right. That feels right. These did... no, there's no point. I don't know which way round these go. So, okay. What we also therefore know is something about these thermos, don't we? Because the low digit in each thermo is going to be the low digit from the 1, 5 pair and the 4, 8 pair. So this square and this square are now selectable from only 2 digits, 1 and 4, and these squares are 5, 8. And they are different. And these are different. Okay. And I might be able to repeat this trick now for this diagonal, where we've got 21 in the middle box. So we need 21 in the orange, but made up of consecutive sequences. So yeah, so one of these has to be 2, 3, 4, adding up to 9. The other one has to be 3, 4, 5, adding up to 12. So one of these is 2, 3, 4. One of them is 3, 4, 5. So the actual options for these digits... Oh, hang on. No, that's wrong. I've made a mistake, haven't I? Oh! No, I haven't made a mistake. I was forgetting this diagonal. Couldn't have a repeated digit on it. And I was looking at the 5, 7 thinking, how can I have a 3, 4, 5? But I can, because I can repeat digits on this diagonal. Phew. Yeah, so one of these is 2, 3, 4. And if it's 2, 3, 4 here, it's going to be surrounded by 1 and 5. And the other one is 3, 4, 5, so that's going to have 2 and 6 around it. So these squares are either 2 and 6 or 1 and 5 again. And again, we can now do the same thing regarding the thermos, can't we? So we know the bulbs is either 1 or 2, and the ends are either 5 or 6. Okay. Okay, so what do we do next? I'm loving this so far. This is one of the most interesting puzzles. Good grief. Okay, now I'm getting stuck though. Is there a way we can tell which way round either these ones go or these ones go? So here we know we're looking at 2, 3, 4 or 3, 4, 5. The other thing actually I might have to keep a track of, it's just occurred to me now, is whether Fibonacci is going to come back into this at some point. Because as I'm learning more about some of these cells, I'm restricting these cells due to the Fibonacci geometry. Don't really like that though, because these on the other diagonal have actually got quite a lot of flexibility. They're selectable from 2, 3, 4, 5, 6 and 7. I'm not sure. This little thermo can't be relevant, can it? This does look like a disambiguating thermo to me. So I'm expecting this one to be used late. It's probably now is the exact time it's going to be used. Now I've said that, but I don't see how I can. It can't have a 9 on it. I mean, that's not interesting. So one of these bulbs is a 1, one of them is a 2. Oh, that's it. Right, okay, goodness me, Simon. Right, one of those digits is definitely a 1. So they're both looking at that digit. That's right, that's got to be right. We know that this is a 1-2 pair, it's just very remote and in different boxes of the Sudoku. But one of them is a 1. And whichever one is a 1 is ruling out a 1 from there. So that's got to be a 4. And therefore that's got to be an 8. Oh, this is going to get us more digits. Because now that's a 4-8 pair. And this now must be a 1-5 pair. And this must be a 1-5 pair. And that means that's the 2-3-4 pair. Or triple. And this is the 5-6-7 triple. So I can see. Oh, I know what I might be able to do now. I might be able to tidy up some of these thermos a bit. Right, let's have a think about that. This is not 4. And this is not 4. But this thermo has to be selected from 5, 6 and 7 now. So we can't put 7 as the second digit. And we can't put 5 as the third digit. So this has come down to being 5 or 6, and this has come down. 5-6 pair in this row means that square's not a 5. So this can't be a 5 now because it would get too high for this digit. So this is 2 or 3, that can't be a 2. This is 2 or 3, this is 3 or 4. And that's just by Sudoku. I've not been assuming anything about which way round this 2, 3, 4, 3, 4, 5 triple go. Right, can we do anything with this one? This one can't see 4 as its second digit because this can't be higher than 4. And that can't be a 2. So now I've got a 2-3 pair in this column. And a 3-4 pair in that column. And this one, that can't be a 5, and that can't be a 2. I'm not sure. Okay. No, I'm not seeing how to do that. Bobbins. Bobbins, that's what I say. Let's go bobbins. Okay. I really don't want to have to pencil mark all of these lockout lines now. Is that what we're going to have to do? I'm not even sure that's going to... I really don't want to do that because I don't know which way round these go. So there's a lot of optionality in these cells. Even if there's a bit less there, that's definitely... These are all high digits. This is a 6, 7, 8, 9 quadruple. Down here, we've not quite got the same. We've got 1s, 2s, 3s and 9s. 6 can't go there. So 6 goes with 2, doesn't it? So that's not a 2 over there. So this can still be 1, 5. This is 1, 5. I'm stuck. I really am stuck. Let's go back and have a look at Fibonacci again. We've got those squares. My colouring is going to go all over. I suppose, yeah, okay, I can get rid of the orange colouring now. The orange colouring is redundant, isn't it? We've done that. The green, I don't remember what the green colouring was, but I don't think we need that anymore. I don't think we need that anymore. So I've now got an uncoloured grid. Right, so let's just have a quick look and see if we can see anything with Fibonacci. We've got this sort of pattern, I think. Now, well, it looks like the blues are a lot more. So the blues. Oh no, I've made a mistake here. I must have made a mistake. Oh no, gosh, I haven't made a mistake. I was just thinking, how can I have an 8 in one of those? Oh! But, well, hang on. This is amazing. Right. I was looking at this 4-8 pair and going, oh, but I can't put an 8 in blue. Now, I admit that is the world's worst scanning because there is an 8 in blue already, so it's absolutely fine for this to be a 4-8. But isn't the point that these two squares always appear in blue in the bulbs? So, oh, this is nuts. So I can actually, right. Let me stop here because this is definitely interesting. I'm not certain it's going to give me a digit, but it's definitely interesting, and I've got to show it to you. So I'm going to prove this. So let's quickly do that. How do we prove that this is true? Let's get rid of the colouring again. Control A, I think, gets rid of my colouring. And I'm going to highlight this box, this box, this box, and this box in blue. I'm going to define now the blue digits. Each box of a Sudoku contains the digits 1 to 9. So these blue cells are 4 sets of the digits 1 to 9. Imagine I wrote each of those digits on a Scrabble tile and I put them in a bag. This is my blue bag of digits. Now I'm going to highlight some cells in orange, and I'm going to highlight 4 different sets of the digits 1 to 9. I'm going to highlight this column, and this column, and this whole row, and this whole row in orange. Now, that's another 4 sets of the digits 1 to 9, but remember that I double count those corner cells in that. And the reason I double count the corners is that this set here of the digits 1 to 9 and this set of the digits 1 to 9, obviously this digit, whatever it is in both of those sets. So in order to create an orange set, or an orange bag that contains exactly 4 sets of the digits 1 to 9, every cell you see must be included, every orange cell you see must be included, and I must put 2 Scrabble tiles in for this one, this one, this one, and this one. And now my orange bag will contain 36 digits, and my blue bag will contain 36 digits, and those digits are identical because they're each 4 sets of the digits 1 to 9. Now imagine I remove this digit from both bags. Let's say this was an 8. I don't know if it's an 8. It could be anything. It doesn't matter what it is. It's definitely in both bags because it's both blue and orange. So if I remove that Scrabble tile from both bags, it's still true to say that my orange bag and my blue bag contain the same digits because they contain the same digits before I took that one digit out, which was the same digit. So I can repeat that, of course, for any cell that has 2 colours. I'm going to deal finally with the corners just so that we can be very clear about how they work. Remember, these corners were double orange, but they were also in blue. So there are 2 Scrabble tiles in my orange bag with this digit in it. Let's say this digit was a 2. There are 2 orange Scrabble tiles in my orange bag and just 1, 2 in my blue bag. So I can take 1 blue out and 1 orange, and of course I'll then be left with 1 orange digit in my orange bag. So each of these actually therefore becomes orange. Whoops. And this gets us to the proof that I was after. So now I have proved what I asserted to be true. I have proved the theorem that the blue cells and the orange cells are identical. They are the same digits. But in this puzzle, this is really, really amazing because the lockout line diamonds definitely, they get mirrored into the blue in each case. Whatever's in these 2 squares ends up on the thermo in the extreme positions. So here I can continue removing digits from my Scrabble bags. I can take these 2 digits out of the orange bag and those 2 digits out of the blue bag because they're the same. So they come out. I can do the same for this lockout line. I can do the same for this diagonal. I can do the same for this diagonal. And all of a sudden, look where we're getting now. We're getting to a point where it's actually almost meaningful. So now we know that these 8 digits in blue are the same as those 8 digits in orange. So, yes. So how can that be a 7? That's definitely not a 7. So this is definitely not a 7. Because if this is an orange 7, I would then know, because of logic, that there must be an orange blue. Where is if this is an orange 7, where is my orange blue? Well, nowhere. These can't be. Where is my orange blue? Did I just say where is my orange blue? I did just say that, didn't I? I'm so sorry. If this is an orange 7, these are the levels of madness to which cracking the cryptic will take you. If this is an orange 7, I need a blue 7. That's what we know. Forget about the blue orangeness. If this is an orange 7, there must be a blue. I almost did it again. There must be a blue 7. Where is the blue 7? Well, it's not in any of these. And it can't be that one because you can't put 2 7s in box 9. So hang on a sec. So that means this square is not a 7, which means this square is the only place for the 7 on in this box now, because we've got 5, 6 pair here. But a C. Yes, but this can't be a 6 either, because if that's a 6, I now need a blue 6, and none of those can be a blue 6, and you can't repeat the blue 6 in there. So that's got to be a 5. That's got to be a 6. Wow. Oh my goodness me. This is one of the great Sudoku puzzles. Now that can't be a 5, look. Which means that can't be a 1. And that can't be a 5. So that can't be a 1. And that can't be a 5. And that is so beautiful. It is so beautiful. because now this is a 2, 3, 4 triple. This is the 2, 3, 4 triple. And if this is the 2, 3, 4 triple, that is not the 2, 3, 4 triple. That is the 3, 4, 5 triple. And where does the 5 go in this triple? It goes there, which means that's a 6. Yeah, well, the fact that this is the 3, 4, 5 triple means we know this is the 2, 6 lockout line, which means that's a 2. This is a 2, 6 lockout line. We might be able to... I'm not sure if I can actually... I'm not sure if I can do that. We probably can, I just can't see how to do it. This is now a 3, 4 pair. But I think we can bounce this back into this one now, because now I know this is a 2, 3, 4 Renban, or virtual Renban. This is a 1, 5 lockout line, so that's got to be the 5, that's got to be the 1. That places a 1 and a 5 on the thermo from the logic we've been looking at. Still don't seem to have repeated digits anywhere, so I'm hoping this is correct. Oh, this 2 is giving me a 3 here. That means that's a 4. That's a 3. That's a 2. I have it. I've done it. I've done it. I've now got my thermos finished. That's a 3 in the corner. That's 3 in the corner. That's 3 in the spotlight, losing its religion. This 4 is beautiful. It sees that square. That's an 8. That's a 4. That's getting me a 1 here. That's getting me an 8 here. This 1 is getting me a 5 here. And that means that must be a 1 there. Now, all I've got to do now is do the 2 and the 6, and we are... It's happy days, isn't it? 8 by Sudoku I can do, actually. The 8's got to go there. Am I really going to have to do Sudoku in this Sudoku puzzle? I fear so. Lizzie, what have you done? Right, okay, 5. Oh, 5 is restricted in this box. 5 has to go there, I think, by Sudoku. Let's click the 5s. Yeah, I can place 5 there. All the 5s are now done. Let's have a look for another useful looking digit. I'm not seeing much at the moment. 1 I can place here. So 1 in this box is on this domino, which I don't think is quite interesting. Oh no, that is interesting. Where does 1 go in box 6? It's got to go there by Sudoku, which places the 1 up here. How many 1s have we got? Loads. I need 1 more. That goes here. Wow. 4. Where does 4 go in that box? It's got to go here. That removes 4 from this square. So 4 is now horizontal in box 5, which means 4 is in one of 2 places in box 4. Oh no, it doesn't. There's a 4 here. Sorry. Now that is bad scanning, but that diamond does make that look a little bit weird. Hopefully you'll accept that excuse. I feel like 2s might be a good place to look. 2s, yes, 2 goes here. Which means there's a 2 in one of 2 places. What about 2s over there? Oh no, that's not so good. Okay, well, let's have a look. I think we might have to get into some proper good living then. We need 6s, 7s and 9s into those squares, with this not being a 6. We might be able to use Fibonacci again, actually, because it just occurs to me that we know the total composition of the blues now, don't we? So we've got 3, 4... Let's try and cancel these out. So we've got 3 and 3, 4 and 4, 4 and... should be another 4, yeah, and 5 and 5. So we've got the options we've got left are, for 4 orange squares, are these ones, 2, 3, 6 and 7. So these squares here have to be, they are a quadruple on 2, 3, 6 and 7. And that's not 3. And that's not, oh bother. I don't think I can eliminate anything from this one. That's not 2. Or 6 actually, that one can't be 6. So this is 3 or 7. Can we eliminate another one there? Not sure. That one can't be 3. So we've got 2, 6, 7. No, sorry, that's useless. Apologies. I was wondering if we could get something done with our old friend Fistemafel, but we can't. So what about these squares? Oh, don't forget the diagonal. Oh, Simon. I forgot the diagonal. That's a 2. That's great. Oh, well, it's not actually great, but it does allow me to move 2 from those squares. Now 2 in this box seems to be fixed, which makes that square a 3. So now I've got a 2, 4 pair going along the middle box. Can I do anything now with this? 6, 7, 8. Oh, I tell you what we can do now. Those squares are all high digits, aren't they? We looked at this earlier, 6, 7, 8, and 9. These ones can't be 8. So that's a sort of 6, 7, 9 triple in that column, which means that square's a 3, which means that square's a 7, and that square's a 6. Yeah, that's a 3 by Sudoku, that's a 9 by Sudoku. These are not 7s, so that square's the 7. This is a 6, 9 pair, so that becomes a 7, 8 pair. This 2 is, oh yeah, there's loads of Sudoku I've not done here. Never mind, we're getting there. 9 comes here, this is a 7, 8 pair. And this thermos, this is probably where this thermo has its moment in the spotlight. Let's just see if we can do anything else. We've got 2s and 8s. Yeah, 8 in this column is done. 8 goes there. 8 goes here by Sudoku. This square's here is a 2. Those 2 squares need to be a 9 and a 4. Don't think that's resolved. This square here needs to be a 3. So there's a 3 here exactly. This needs 2 here exactly. 2, 4, 4, 9. That 9's going to reflect up here along with a 7. That finishes the 7 and the 8. The 9 and the 6 get done. My goodness me. Now I'm going to look at this. This is a 7, 8 pair and it's resolved. Yes, it would have had a deadly pattern. This 7, 8 and this 7, 8. So the fact that this thermo exists tells us the order of that 7, 8, which in turn tells us the order of those 2 squares. And we still need a 6 here by Sudoku. That finishes the 6, 9, the 9 and the 2. Now this is a 7, 9 pair, which we can do. And this needs to be a 3, 8 pair, which we can also do. And it looks correct, doesn't it? Tick. No! Oh no, I've put 2 8s in this box. Is that a slip of the... No, that needs to be a 6. Why did I think that was an 8? Let's just click tick. Oh, it's still not right. Oh no, I've gone completely awry. Oh no. Hang on, let's see. How far do I have to go back to realise what I've done wrong there? Oh no, it's miles. It's miles back. I've put 2 8s in this box down. Oh, I remember when I did this. I think I probably misscanned this, didn't I? Is that what I did? What a wally. Okay, so let's come back and check. 8, 8, that is an 8. That's an 8, that's a 7. That looks fine. That's now a 2. How on earth did I put an 8 there when there's an 8 there? That is a mystery. This 7, 8 still is correct. That's an 8, that's a 7. Ooh, okay. This 6 is doing the 6 and the 9, so that's all very doable. This is a 2, 3 pair. And this is a 7, 9 pair, which is resolved. Yeah, this is unwinding a little bit differently now, isn't it? So I clearly did make an awful error. Apologies. 7, 8. And this is a 3 and 9, which we can do. And this square now is known. That's got to be a 6. That fixes the 6 and the 9. Gives us a 9 here. This should be a 2. Okay. Just need to figure out this bottom bit. 3 and 5. Well, that's doable. And that fixes the 3 and the 2. The 2 and the 4. The 4 goes for 2 5s in now. Simon, stop it. I think that was a misclick. That was a misclick. I protest. Yeah, that's a 6. That's a 3. That's a 3. That's a 2. That's a 2. That's a 4. That's a 4. And that's a 9. Now, yes. Okay, a little bit of a ricket at the end of an hour's solve, but hopefully you'll forgive me. That's just fatigue. It's fatigue at the end of being battered around the head by this brilliant, brilliant puzzle. 4 lockout lines. Lizzie 01, take a bow. That is one of the great Sudokus. It really is. I mean, it is magical that that has a unique solution. And more magical is how gorgeous the solve path is. These lockout lines do absolute wonders when combined with the thermos. It's such an original execution. And, you know, just the way that Lizzie's had the thought, you know, I can force 1 into this string of digits in the middle box. And if I can force 1 into these string of digits by introducing the diagonal, then with an arrow, I could force this arrow to be a 2, 3, 4, 9, and that in turn can affect the way the rem bands get built along the diagonals. There's so much cleverness in this. I mean, I'm sort of barely able to appreciate and articulate it myself, but I can feel it. It is just stunning. Absolutely loved it. Really did. Let me know in the comments how you got on with this one. This is a gem. And we'll be back later with another edition of Cracking the Cryptic.